Welcome to this video on the T20Q144 i4 FPGA development board. In this video, we will walk you through the complete design-to-demo journey of our FPGA platform. We'll begin by discussing the important features of the FPGA and why this device was chosen for the development board. Next, we'll move into the schematic design, where we explain the key building blocks of the board and the design considerations behind them. After that, we'll take a detailed look at the PCB layout, followed by a close view of the fully populated board, highlighting the major components and interfaces. Once the hardware is covered, we'll guide you through the software installation process, step by step. Then, we'll write a simple test program to blink the onboard LED, giving you a first hands-on experience with the FPGA. We'll also show how to download the compiled design into the platform flash, so the FPGA can boot automatically on power-up. Finally, we'll wrap up with a live demonstration, showing the board in action. By the end of this video, you'll have a clear understanding of both the hardware and software aspects of this FPGA development board. At the heart of this development board is the T20Q144 FPGA from Efinix belonging to the Trion FPGA family. This device offers 19,728 logic elements, which is more than sufficient for a wide range of applications, from digital logic experiments and embedded controllers to signal processing and communication projects. In terms of memory, the FPGA integrates over 1 million bits of embedded RAM, allowing you to implement buffers, FIFOs, and small processors directly inside the FPGA without any external memory. The device provides 97 general-purpose I/O pins, giving excellent flexibility for interfacing with displays, sensors, ADCs, DACs, communication modules, and custom expansion boards. The core operates at a low voltage of 1.15 to 1.25 volts, ensuring low-power operation while maintaining reliable performance. One of the key highlights is its industrial-grade operating temperature range, from -40 degrees Celsius to +100 degrees Celsius junction temperature, making this board suitable not only for academic labs but also for real-world and industrial prototyping. Finally, the FPGA comes in a 144-pin LQFP package, which strikes a good balance between compact size and easy PCB assembly, especially important for educational and in-house development boards. Power supply pins and decoupling capacitors. Let us now look at the power supply pins and decoupling capacitors of the FPGA. The figure shows the FPGA pins used for providing the required supply voltages. In this design, there are three main supply voltage domains. The first is 3.3 volts, which is used to power the I/O lines, also referred to as VCCIO. This voltage determines the logic levels for external interfacing. The second supply is 1.2 volts, which powers the FPGA core, known as VCC. This supply is critical for the internal logic operation of the device. The third supply is also 1.2 volts, used to power the analog sections of the FPGA, such as the phase-locked loop, or PLL. A common ground is used across all supply domains. You may notice that the FPGA has multiple power supply pins, even for the same voltage. This is because different internal blocks of the FPGA draw current simultaneously, and multiple pins help reduce voltage drop and noise. To ensure stable operation, power supply decoupling capacitors are placed close to each supply pin. These capacitors play a very important role by supplying transient current, reducing high-frequency noise, and maintaining voltage integrity during fast switching events inside the FPGA. For the analog supply, AVCC is generated by filtering the core supply VCC using an LC filter. This helps isolate sensitive analog circuits from digital switching noise. All the decoupling capacitors used in this design are multilayer ceramic capacitors, or MLCCs, in the 0805 package, which offers a good balance between capacitance value, performance, and ease of assembly. Next, let us look at the low dropout regulators and the onboard clock source used in this design. Power to the development board is provided through a USB connector, which supplies 5 volts. This 5-volt rail serves as the primary input supply for the entire board. The first stage of regulation converts 5 volts to 3.3 volts using the LD1117S33 low dropout regulator. This 3.3-volt supply is used to power the FPGA I/O banks and other 3.3-volt peripherals on the board. The output of the 3.3-volt regulator is then fed into a second LDO, the LD1117S12, to generate 1.2 volts. This 1.2 volt supply is used for the FPGA core and other internal blocks that require a lower operating voltage. For stable operation, both regulators are provided with appropriate input and output capacitors. These capacitors are essential for regulator stability, noise filtering, and transient response. Moving on to the clock source, the board includes an onboard 50 MHz oscillator. This oscillator provides a clean and stable clock signal required for synchronous operation of the FPGA. The oscillator output is a clock waveform with a 3.3 volt swing, and it is directly connected to the PLL input of the FPGA. This allows the internal PLL to generate multiple clock frequencies as required by user designs. Next, let us look at the platform flash interface used on this FPGA development board. The FPGA configuration is stored in an external serial flash memory, specifically the W25Q16 device. This is a 16 megabit SPI flash memory that stores the FPGA configuration bitstream in non-volatile form. During power-up, the FPGA automatically reads the configuration data from the platform flash and loads it into its internal configuration memory. This process allows the FPGA to start running the user design immediately after power is applied, without requiring any external intervention. The platform flash communicates with the FPGA using a serial peripheral interface, or SPI, which uses clock, data, and chip select signals for reliable configuration transfer. Pull-up resistors are provided on the interface lines. These pull-ups ensure defined logic levels during reset and power-up, improving reliability and preventing unintended behavior. To provide flexibility, connector J2 is included on the board. This connector allows the platform flash to be programmed using an external programmer, if required for development or recovery purposes. It is important to note that the FPGA must be held in reset while programming the platform flash. This prevents bus contention and ensures correct programming of the flash memory. For this purpose, pins 5 and 6 of connector J2 should be shorted, which places the FPGA in reset mode during the flash programming operation. Once programming is complete and the reset is released, the FPGA will reload the new configuration from the platform flash and begin normal operation. Now, let us look at the platform flash programming circuit provided on the development board. The board includes an onboard flash programmer implemented using the CH341A USB interface IC. This IC allows the platform flash memory to be programmed directly from a PC, eliminating the need for an external programmer during normal development. The CH341A on this board supports two distinct operating modes, which are selected using Jumper J7, and it is important that this selection is made before powering up the board. In the first mode, the CH341A is configured to program the platform flash. To enable this mode, Jumper J7 is shorted before power is applied. In this configuration, the CH341A communicates directly with the flash memory to download the FPGA configuration bitstream. In the second mode, the CH341A operates as a USB to UART converter. To enable this mode, Jumper J7 is left open before power-up. This allows serial communication between the PC and the FPGA for debugging, logging, or user-defined applications. In UART mode, the transmit and receive lines of the CH341A are connected to 135 and pin 131 of the FPGA, respectively. These pins can be used for serial data exchange once the FPGA is configured. The CH341A programmer software is used on the PC to download the configuration data into the platform flash. After programming is complete and the board is reset, the FPGA loads the new design from flash and starts operating automatically. Next, let us look at the LED section provided on the development board. The board includes 8 LED indicators, each connected in series with a current-limiting resistor. These resistors protect the LED indicators and ensure safe operation when driven from the FPGA I/O pins. All 8 LED indicators are terminated on Berg connector J3, which makes them easily accessible from the FPGA. Using jumper wires, these LED indicators can be connected to any GPIO pins of the FPGA, allowing complete flexibility in pin selection. This arrangement is especially useful for testing, debugging, and demonstration purposes, such as verifying GPIO functionality, displaying logic states, or running simple test programs like LED blinking patterns. Next, let us look at the general-purpose input and output pins of the FPGA. The FPGA GPIO pins are brought out to Berg connectors, making external interfacing simple and flexible. Specifically, the GPIOs are available on connector J4, which provides 26 GPIO pins, connector J5 which provides 23 GPIO pins, and connector J6 which provides 35 GPIO pins. In addition to the signal pins, ground connections are also provided on these connectors, ensuring a proper return path for external signals and reliable operation. All these GPIO pins are 3.3 volt compatible, allowing direct interfacing with commonly used sensors, displays, modules, and laboratory equipment without additional level shifting. Next, let us look at the provision provided on the board for connecting a digital storage oscilloscope, or DSO. Connector J10 consists of 4 pins, all of which are connected to ground. This allows the ground clips of the DSO probes to be connected securely. With this arrangement, grounding for 2 oscilloscope channels can be done easily and reliably. For the signal connections, connector J9 is provided for channel A of the oscilloscope. J9 has 4 shorted pins, and this connector is left floating, allowing it to be connected to any signal of interest. Similarly, connector J11 is provided for channel B of the oscilloscope. It also consists of 4 shorted, floating pins, making it easy to route signals to the second oscilloscope channel. Using jumper wires, J9 can be connected to any FPGA GPIO pin, and J11 can be connected to any other GPIO pin. This makes it very easy to change the signals being observed during testing or debugging. With this approach, changing oscilloscope probes is not required. This is particularly useful because some FPGA GPIO pins may be difficult to access directly using standard DSO probe hooks. Overall, this arrangement greatly simplifies signal observation and improves convenience during laboratory experiments and development work. Let us now take a look at the top view of the development board. The image shown here is of the unpopulated printed circuit board before component assembly. This view helps in understanding the overall layout and component placement strategy. On the top side of the board, the main integrated circuits are placed, including the FPGA, the platform flash memory, and the USB interface IC. In addition to these, the locations for onboard LED indicators, Berg connectors, and other interface connectors are also visible on the top layer. This placement is carefully planned to keep signal paths short, simplify routing, and make the board easy to assemble and debug. Viewing the unpopulated board gives a clear picture of how the functional blocks are organized before the components are mounted. The corresponding populated printed circuit board is shown here. All the components discussed in the schematic and layout are now assembled on the board, including the FPGA, platform flash memory, the USB interface IC, and the supporting passive components. Let us now look at the bottom view of the board, shown here in the unpopulated state. This view highlights several important support components that are placed on the bottom layer of the PCB. The locations for the low dropout regulator ICs, the onboard oscillator, and the power supply decoupling capacitors can be clearly seen. Placing these components on the bottom side helps in optimizing board area, improving routing efficiency, and maintaining a clean layout around the FPGA on the top side. This bottom side component placement also helps keep sensitive power and clock circuitry close to their respective loads, which is important for reliable FPGA operation. The corresponding bottom view of the board in the populated state is shown here. The low dropout regulator ICs, the onboard oscillator, and the decoupling capacitors discussed earlier are now assembled on the PCB. Let us now move on to the testing of the regulated power supplies on the board. First, connect the development board to the USB port of a PC. which provides the required 5-volt input supply. Once the board is powered, use a multimeter to verify the regulated output voltages. Check the 3.3-volt rail, which powers the FPGA I/O sections and other peripherals. Next, check the 1.2-volt rail, which supplies power to the FPGA core and internal logic. Confirming these voltages ensures that the power supply section is functioning correctly before proceeding with FPGA configuration and further testing. This completes the power supply verification of the development board. With the 3.3-volt and 1.2-volt rails confirmed, the board is now ready for FPGA configuration. In the next video, we will proceed with FPGA programming and functional testing.